Hi, I'm Chris Johansson.
And I'm Alex Vanderloop.
And we're members of the OpenUAS research project. So let me start off with a hypothetical for you. Let's say you're a research team that is researching how to extend capabilities, autonomous capabilities for fixed-wing craft, or looking to extend the capabilities of sensors on fixed-wing craft, or looking to how autonomous vehicles interact with each other while in flight. Or let's say you're a member of a high school team and you're just interested in learning how fixed-wing crafts are put together, and you're interested in the hobby and how different specifications and characteristics of flight might interact with each other. Well, there's a number of options available to you if you're looking to do that. Unfortunately, it's not quite like a quadcopter where you can just pull designs straight online, put together a fixed-wing aircraft within a week. It's much more arduous than that if you're looking to build your own. So in terms of the options available to researchers today, one half of the options might be a commercial option, like the Albatross above me. This is offered by Applied Aeronautics. It's about $6,000, so very cost prohibitive for any research teams or high school teams looking to put together a fixed-wing craft. It's very roomy. The fuselage is very roomy, so you can put any sort of sensors you want to put in there, so that's very nice. Very large wingspans, very large craft. It flies very, very well, albeit a little unwieldy and a little difficult to fly, so some pilots might not be so willing to fly it. And one of the knocks of it is that it's very difficult to repair, so if the wing gets nicked or something goes wrong, it's just an arduous process to repair. So it's very cost prohibitive, and it's just not going to be an option for most teams.
On the other hand of the spectrum, we have the E-Flight Apprentice here. So some of the perks of this model is that it is significantly cheaper. It's more of a hobbyist option, costing only a few $100s. And additionally, it is very nice to fly just because, once again, it is that hobbyist option. But it also has its drawbacks. One of the first ones I'd like to note is it doesn't have quite the space in it that the Albatross has. So if you were trying to add other sensors, or if you were concerned about heat buildup within that body, then that could become a real problem. Additionally, this also has the difficulty of repair if there are any damages. So if you get some damage to your rudder, you have to order the entire tailpiece if you were trying to repair it. And once again, for the wing, if there is a break, then you have to order the entire wing. And so that can make it very difficult if you were to crash or if you were just trying to test things out. So one of the reasons that this happens for most UAS is because they get phased out so quickly. Even previous versions of this Apprentice are already being phased out. So the purpose of this research project is to create a well-documented open source fixed-wing aircraft so that anyone can use it for research applications or sensor testing, or even just the high school teams that are interested in it. So what we want to do is, like I said, make it open source that people can do whatever sensors and testing, and also make it well documented so that if people want to modify it or keep it up to date, they can do that and look at any point in our process what we did and why we made those decisions. Through our presentation today, we're going to have our subsystems talk about how they went about designing and manufacturing our current version of the fixed-wing aircraft, and then we're going to take a look at the flight test of our actual finished version.
Hello, I'm Stephanie Joe.
I'm John Edgren.
And today we're going to talk to you about the design of the OpenUAS version 1.0, also known as Veronica. In here you can see that our OpenUAS has a fuselage connected to the tail with a tail boom made from carbon fiber. This is basically for two reasons. One being weight, as we want to reduce the weight of the OpenUAS, and two, we want also to have the capability of hand launching. If we go into some more specifications of the OpenUAS, we have a 6-feet wingspan and a 38-inch nose-to-tail distance. Additionally, we have a 2-degree dihedral angle for the wings. And if we go into more in-depth of the wing, we have the Clark wide airfoil profile. This was selected after doing some iterative analysis using SFLR5 and some validation on its static stability with AVL. Additionally, for the OpenUAS, we did some CFD analysis over with STAR CCM. If we go into the tail pieces, we have the symmetric NACA 0012 airfoil for both the vertical tail and the horizontal tails. This is basically due for the thickness and manufacturing process. Now I'm going to pass it on to John, who will talk to you more about the fuselage.
So for our fuselage, we decided to go with a rectangular cross-section, partly for ease of manufacturability, and also so our electronic sled can slide in and out of the fuselage very easily. Speaking of our electronic sled, that contains all of our electronics except for the motor, ESC, which are located on the nose cone, and then the servos for the wings and the tail. On the electronic sled, we also have our battery that we have located towards the back side of the electronic sled to have it about at the quarter cord point on the wing, so changing out batteries won't affect our CG very much. We also can move the battery forward and back a little bit if we want to change our CG. And then Stephanie mentioned earlier that we used a hand launch technique. And we did that for our first test flight, and that worked well. But we also wanted to implement landing gear on the UAS so we could use runway, solid surface, or grass. And so for that, we used a conventional landing gear setup with the two main wheels in the front and a tail wheel in the back. We did that mainly to save as much weight as possible, and also that it'd be easy to implement onto the current design, and wouldn't use an extra servo that we would need if we wanted to have in control of the nose wheel. Also, when we added the landing gear, we added a rudder extension and made the rudder a little bit bigger to have a little bit more control on those slow speeds when we're taking off and landing, which has worked pretty well so far. And now I'll pass it off to the manufacturing team to talk about how they built the UAS.
Hi, I'm William Birkin,
I'm Evelyn Moyer.
And I'm Taylor Rocky.
and this is the manufacturing sub-team of the OpenUAS research team. Here you're looking at Veronica. As you can see, most of it is made out of carbon fiber. The reason we chose carbon fiber is due to its high strength to weight ratio, which gives it very desirable characteristics. The way we use carbon fiber was we made molds out of XPS foam, as you can see here behind us. The reason we chose XPS foam is because it's very cheap, easy to work with, and easily available at any home improvement store. Once we got those 3D molds out of the foam, we did carbon fiber layups over top of them using regular carbon fiber as well as some West Systems epoxy resin. The reason we chose that is due to very desirable characteristics for strength and weight. Beyond that, we use a lot of JB Weld epoxy for general epoxying materials, as well as super glue in certain areas. As you can see, carbon fiber nose, body, wing, tail boom, and then some tail pieces. In this iteration, you can see it is some foam tail pieces as well, coated in epoxy for extra strength. In the past, we have tried to use 3D printed parts, but in this current iteration, we wanted to move away from that due to the fact that 3D printed parts can add quite a bit of weight to the model. Now I hand it off to Taylor.
So during the process of manufacturing Veronica, we first started with the body and the nose cone of the OpenUAS in order to allow for a better transition off to the electronics team to do work when we finished up working on the wings and tail pieces. With the wings, we first started with 3 pieces, but it came together with 1, and we also created the ability to interchange out wings pretty easily. We're looking for other options to do that for the tail pieces, but as of now, they're currently just epoxied. So Evelyn can talk a little bit more about that.
Yeah, so our wing design has 3 main components. We have a left and a right wing, and then this centerpiece, which gets bolted into the main fuselage. So in this iteration, our wings are, as Will said, foam, CNC'd, and then with a carbon fiber layup on top of them. And what we found really beneficial about that carbon fiber layup is that we did each piece individually, and then when we went to epoxy them together, after that epoxy had dried, we could go back and do another layup centered around this middle part where all of the seams are to add extra strength to what would have been a weak point. The other thing that we like to highlight on these wings is that the ailerons are from the original wing layup. So what we did is we laid up the whole wing and then cut these pieces out individually, and that allowed us to get that smooth finish without having to do 2 separate layups and risking some sort of errors. Additionally, in our next iteration of design, we are looking to completely get rid of this carbon fiber because it is expensive and it's difficult to work with if you don't have the correct safety precautions and procedures and places to work with it. So we're looking at potentially making wings out of just the foam, not putting the carbon fiber on, but still using that epoxy in order to give it the strength that it needs.
Now to hand it off to the electronics team.
I'm John Lewandowski. I'm the team lead of the software and electronics team.
And I'm Colton Glick.
And I'm Ellie Dearson.
I'm Marcy Anderson.
So this is our electronics slate. It has a 2-shelf layout designed to fit the U.S. electronic system, which we call the Iron Bird. Multiple sizes of battery varying from 3,000 milliamp hours all the way up to 7,600 milliamp hours, as well as space for a test payload. For example, here we have a companion computer, Raspberry Pi. The electronics and battery are mounted using Velcro strips, which allows end users to adjust the center of gravity of the OpenUAS depending on the user's test payload. The core of the Iron Bird includes the Pixoc 4 flight controller. Pixoc uses the PX4 flight stack, which is an open source flight software that is highly configurable, well documented, and already has many features already implemented, including flight logging and stabilized flight modes, which helps with flight testing. The Pixoc also allows for direct interfacing with custom payloads like companion computers and FPGA, such as the Raspberry Pi, allowing users to test flight software and other custom sensors. The Pixoc communicates with the ground station on a laptop, allowing for flight monitoring and logging. So for motor and props, MotorCalc 8 was used to simulate thrust available for different motor and prop combinations. It also output current draw depending on as a function of thrust. This was done over varying speeds. The data was then compared to the thrust required calculated from CFD to determine the most efficient prop and motor combination. After combination was selected, thrust as stand was used to validate the theoretical data. An ESC was then selected to match the max current draw calculated from the data.
Alright, so our setup that we have here is the most basic setup you can have. We have our Pixoc 4, which communicates with all the pieces that are on the electronics bay and the interfaces across the whole UAS, like our ailerons and our flaperons and everything there. And we have a Tyrannus DX8 radio transmitter and receiver that's able to communicate with our controller if we have controlled flight going on, and then we have a transmitter that goes to our Q ground control station on our computer so we can get our log test data from that. And we also have our battery and a GPS module that is not included on here because it's on the outside of the model. And now to Colton for our simulation.
Right, so this year we've been working on developing our own custom version of the PX4 software. In order to do this, we forked the official version of PX4 onto GitHub into our GitHub repository. This allows us to create a customized airframe, which gives us the ability to directly program our parameters into the source code, making it easier for other users to utilize our tuned configurations. Some of these parameters can include PID gains and LiDAR settings. Additionally, with the custom version of the PX4 software, we've been able to develop a simulator in order to test new features of the UAS and to train new pilots. This provides us a fast, safe, and cost-free way in order to accomplish all these things while keeping everything custom and tracked on our GitHub page. Now over to Marcy for future work.
So in the immediate future, we're looking at adding a downward-facing camera and a LiDAR sensor, which will help get a velocity estimation using computer vision and optical flow. But one of the nice things about our setup and about the PX4 is that it's super modular, and so we can add these things and remove them as we see fit for different test flights. And also people who make this in the future and use our work can add and remove different sensors that they see fit that are compatible with the PX4 as well. And now to John E. to talk about the test flights we've done.
For the first flight of the OpenUAS, we had not yet incorporated landing gear, so we used a hand launch technique. And the hand launch technique worked very well, and the UAS climbed out exceptionally well and had plenty of power. In the air, the OpenUAS was not as stable or as easy to fly as we would have hoped, however it was very maneuverable. Additionally, using stabilized mode on the Pixhawk 4 made the OpenUAS considerably easier to fly and still was very maneuverable. In later test flights, we also added the landing gear and increased the size of the rudder for better controllability at low speeds. And we also tested a second wing design, which was a NACA 23012 airfoil, and that really had no significant changes on the flight characteristics of the OpenUAS. We have crashed the OpenUAS twice, and it has sustained limited damage in the crashes and was also very easily repairable both times. Additional tests we have performed have been to test the stall and cruise airspeeds of the OpenUAS, which we have found to be about 12 meters per second and 23 meters per second respectively. So far we've flown the OpenUAS for as long as 15 minutes on one battery at an average power setting of roughly 85%. Future iterations of the OpenUAS designs will work to improve the stability of the aircraft as well as increasing range and decreasing the stall speed. Now to conclude the video, Chris and Alex.
All right, so to wrap some things up and go over what we saw today, we saw that there's no currently available open source, highly documented fixed wing aircraft available. We have presented a solution to that, a small reconfigurable UAS which meets the specifications of being open source and highly documented. Our design relies mainly on CNC foam pieces with carbon fiber layups, and that will be changed in the future.
And additionally, we have an electronic system that is verified to work with our current iteration of the UAS, as well as providing a version-specific extension to the PX4 firmware. And finally, we have shown flight test capabilities that have proved the capabilities of our current version, as well as showing areas for further improvement. So thank you for listening to our presentation. If you have any further questions or want more information, feel free to reference our report. Thank you.